Hi. The practical calculation of derivatives is quite simple thanks to some rules that are easy to remember. Often, however, these rules end up being applied mechanically without enough thought. Since the devil is in the details, it is essential to pay close attention when using calculation rules. In this video, we aim to better understand what the derivative calculations rules are, what they exactly state, and what their limitations are. First of all, let's focus on algebraic rules. Let f and g be two differentiable functions at a generic point x. Then we have that their sum difference is differentiable, and the derivative of the sum difference is the sum difference of the derivatives. More or less the same happens with the product, so the product f times g is differentiable. However, the derivative of the product is not the product of the derivatives. It is a bit more involved formula. It is the first factor derivative times the second plus the first factor times the derivative of the second. And similarly, we have a formula for the ratio. Now, this formula comes from the rules of calculus of limits. So let's show how this happens in the case of the product. The first starting point is to write the incremental ratio for the product, or in an expanded form, this. Now, the point is to try to recognize here the incremental ratios of f and g. This would be possible if we could factorize, for example, this factor g of x, but you see it's not the same for the two. So the trick consists in reworking this expression to make this possible. And here what we do, we take, for example, this factor, f of x plus h, and we add and subtract f of x. Then we put together f of x plus h minus f of x, and we split the fraction. What happens is that we get f of x plus h minus f of x divided by h multiplied by g of x plus h that you see here. Now, the first part is the incremental ratio of f that goes to f prime of x when h goes to 0. And the second factor is g of x plus h. Now, since g is differentiable, it is well known that it is continuous. So, in particular, g of x plus h will go to g of x when h goes to 0. Then we have a second part of the story, which is this f of x that factorizes and multiply this fraction at g of x plus h minus g of x divided by h. This factor now goes to g prime of x, and this is where the product rule comes from. Now, the other rules are similar. The proof of the sum difference is very easy, while that for the quotient is slightly more intricate. Why not give it a try? Now, from these rules, two other very useful rules follow. The first one is the so-called linearity of the derivative. It says that the derivative of the linear combination of two functions, so something like constant times function plus constant times function, is the linear combination of the derivatives. Another important formula is the derivative of the reciprocal. So far, everything seems simple. However, as mentioned, there are some common mistakes. For example, suppose we want to determine whether the function phi of x equal to absolute value of x minus the root of e to x squared minus 1 is differentiable at x equals 0. What do you think about it? A classic error is the following. I know that modulus of x is not differentiable at x equals 0. So also the function phi, which includes the modulus of x, cannot be differentiable. The error in this incorrect, we repeat, argument is logical in nature. So, indeed, the rules state that if I have two functions f and g that are both differentiable, then their sum is also differentiable. What they do not say is that if one or both terms are not differentiable, This does not imply that the sum is not differentiable as well. And this is false. We can understand it by a very, very simple example. Take as two functions the modulus of x for f and for g minus the modulus of x. In this way, they are both non-differentiable at x equals 0. But what happens when we sum these two? We get identically 0, so something which is differentiable at x equals 0 and everywhere else. A similar remark holds for the product. Can I say that if one or both factors are non-differentiable at some point, then also the product is non-differentiable at that point? No. And the example is basically the same. Take the modulus of x as for f and for g. It is not differentiable at 0, so the two factors are not differentiable. But when you multiply, what happens is that you get x squared, which is differentiable at 0. So the point is that if the assumption of the rule are not met, the rules cannot be applied, quite simply. So in these cases, how do we determine if the function is differentiable, and how do we calculate its derivative? Let's see this in the case of the proposed example. So here, to check the differentiability at x equals 0, we need to calculate the limit for h going to 0 of phi 0 plus h minus phi 0 divided by h. Now, phi of 0 is equal to 0, and phi of h is equal to phi of h. So we have the limit for h going to 0 of absolute value of h minus root of e to h squared minus 1 divided by h. Now, since we have this modulus of h, it is perhaps convenient to split this limit into left and right limits. So for the right limit, we have limit for h going to 0 positive of fraction h minus the root divided h. So we divide this fraction, and we have the limit for h going to 0 positive of 1 minus. Then I can carry this h inside the root. It is positive, so I get root of e to h squared minus 1 divided by h squared. Now here you should recognize the structure of a fundamental limit, e to t minus 1 divided by t when t goes to 0. This quantity goes to 1, and therefore the root will go to root of 1 because of the continuity of the root, and this means that the limit is 0. So this means that the right derivative of phi at 0 exists, and it is equal to 0. What changes if we now compute the left limit? So limit for h going to 0 minus. Now, the modulus of h becomes just a minus h, so minus the root divided by h. So this becomes the limit for h going to 0 minus of minus 1. And now I cannot carry the h inside because h is negative. So there will be an error here. But if I put the minus here, minus h is positive. I can do with minus h. So I will have plus root of e to h squared minus 1. Now the minus h goes inside as minus h squared, so again h squared. And similarly as before, the root goes to 1, and therefore everything goes to 0. So this means that the left derivative at 0 exists, and it is equal to 0. Conclusion: since the left and the right limit both exist and are equal to the same value, 0, this means that the full derivative of the function exists, and it is equal to 0. In short, if the rules do not apply, don't panic. We have always the definition. Great. Now it's your turn. Well, practice the calculation rules, which are a quick, efficient method for computing derivatives, and also tackle some more delicate problems where the rules might fail at some point. Finally, reflect on some abstract consequences of the rules, like on this question. Good luck.